This is the Applied Statistics in Healthcare series, and this is the fourth session of the multiple linear regression course. In week 4, we're going to look at the first set of case studies, and these will cover the topics of hypothesis testing, effect size measurement, and predictive modeling. We'll do 2 models. The first would fall under predictive modeling. The topic is maximum forced expiratory volume. It's a breathing test. And in the second half, we'll look at hypothesis testing and effect size. We'll do that in an explanatory model of very low birth weight. Let's begin. Okay, for our first set of case studies, we'll look at hypothesis testing, effect size measurement, and predictive modeling. For this first model, we'll do a predictive model, and we're looking at forced expiratory volume. And for a second, we're going to do an explanatory model, and that's very low birth weight. For predictive modeling, the topics we're going to look at are relaxing the assumptions of linearity and additivity. We'll do a validation of calibration and discrimination. We'll produce a nomogram. We'll also do a decision curve analysis, and based on selecting a cutoff level. And so in our first study, we'll do the pediatric forced expiratory volume study, or FEV. We have a sample size of 654. Our variables are FEV, which is the maximum forced expiratory volume in 1 second, age, height, sex, and an indicator on smoking, whether they're a current smoker or non-current smokers. We will first examine descriptive statistics of the average FEV outcome by categories and by quartiles of continuous variables. Looking at descriptive statistics is a powerful tool to spot trends in the data and for model development. For example, large jumps in rates for quartiles can signal nonlinearity. And just as a reminder, this is on pediatric FEV scores. So we're looking at those under 18 and the volume of air that they can exhale in 1 second. So here's a set of descriptives. In the top, we have age, and we're looking at the means of our FEV. Because age is a continuous variable, we have these broken up into quartiles. And we see what looks like a linear trend. We see for the age groups of 3 and 9, they're lower than this red dot indicates with the averages, and that's below 2. FEV ranges from about 1 to 4 in this data set. And we see that for 3 to 9-year-olds, they're on the lower end. When we look at 9 to 11-year-olds, they have an increase of almost about 2.6. And that large jump in rate can signal nonlinearity. So we have a nice linear trend, but we see the biggest, or what potentially is the biggest jump between that first and second quartile. And then when we look at the average rate for 11 to 13-year-olds, that's further to the right. They have over a value of 3. And when we look at 13 to 19-year-olds, they do have the highest average FEV rate over 3.5. We see a similar trend for height. We have, again, heights measured in inches, and it's a continuous variable. We have the 4 quartiles, and we see an increasing pattern which suggests linear trends for continuous predictors, especially for height. And when we look at sex, we have 2 categories. So we're looking at the difference between those 2 groups. We see females have a lower FEV while males have a higher FEV. And we see in the categorical variable smoking, whether they're a non-current smoker or if they're a current smoker. We actually do see the non-current smokers having a lower FEV while the current smokers having a higher FEV. And it's important to note that most of our smokers are in their mid to late teens, so we do have an age difference in there. And overall, we do see the average FEV is about 2.6 in this data set. Okay, so now we're going to look at different models. We have a linear and additive model summary on this slide. The model is FEV equals age plus sex plus height plus the smoking status. And we get a prediction formula for our data for this linear and additive model. We see that first value of negative 4.456 as our intercept. And then to get a predicted score for a predicted FEV score based on these coefficients and values, we would then add the product of the age regression coefficient by the actual age, and that's the unique age value of each respondent in this data set. And then we would add that with the coefficient for sex, and then we would do the same for height and their smoking status. So this is a regression. This is the regression formula that we can use to get predicted scores, but this also is based off the regression results. So we can see how these values in this formula that calculates a predicted score has unique components, and we can see what those coefficients are, and we see how they match up with the formula, and as well as getting the significance level that we see on the far right to see if the trend or the difference for the categorical factors, if they're significant. We're using the standard definition of an alpha level of 0.05, so we can see that age, the sex indicator, and height variable, they are all significant at that p's less than 0.05 alpha level. Our smoking status doesn't seem to be significant, but that we feel that's an important predictor, so we're going to keep it in. And now we're going to compare different models. We just looked at the linear and additive model, which is on the top row. We can see the different variables: age, height, sex, and smoke. And now we're going to look at different models. We have an interaction model, and that's between age and sex. We have a nonlinear model, which is allowing nonlinear terms. In this example, we're going to use splines, but you can also use a polynomial model or a quadratic model specifically, where we used a squared term for age and height. You can do that as well, but in this example, I'm going to use splines, which are nonlinear terms similar to polynomial models. And we also have on the bottom a nonlinear and interaction term, where we have both nonlinear terms and interactions between age and sex. So when we look at the top row, we see we have reported the R-square. We have a validated R-square. We're going to look at validation, some model validation results later. But I use that same process to get a validated R-square to see how that holds up and how it deals with the possibility of overfitting. And then we have the AIC, a Kaike information criteria, and it's important to remember that a lower value is better. So now we can just begin to look at the models. We see that relaxing the linearity assumption by using a nonlinear term for our predictor increased model performance the most. So the biggest jump in R-square is seen when we add in that nonlinear term. It jumped up from 0.775 to 0.798 in comparison to the interaction term that increased to 0.784. So we do see a lot of benefit from having a nonlinear term, because often we do see not a nonlinear pattern or trend between your outcome and a predictor. And we certainly see significant interactions, but I would say that it's more often that you're going to benefit from a nonlinear trend. That seems to happen in most models, while a significant interaction can happen in some models. Not most. I guess it depends on what area you are focused on or what things you're studying, but in general, a nonlinear term will benefit your model more often than an interaction does. So it's not surprising to see that we have a bigger benefit after introducing that nonlinear term. But doing both, as we see on the bottom, gives you the biggest R-square. And when we look at validated R-squares, again we see the biggest value is for that nonlinear and interaction term. The values are validated R-square is 0.796, rounds up to 0.80, and that's a very high level of R-square. And it's important to note that some things are a lot more predictable than other things. Something that may be the result of your physiology, such as how much air can you exhale in 1 second. Those may have things that are a lot more predictable than other things, such as personal choice, a chance occurrence, such as requiring acute care treatment, an infection, sepsis. Those are really tough things to predict. And there's varying degrees. Something that's strictly along the lines of physiology, or even things mechanical, such as miles per gallon, which we have seen in the past 3 weeks. Those seem to be more predictable. So it's important to know what are realistic expectations in terms of what kind of R-square you're going to shoot for. If you're doing something that's a lot more predictable, then you'd expect that you'd get a better R-square out of your model. And it's also important to say, okay, well, if I'm going to get a lower R-square, what can I do with that data, and what can I do with a model? We'll see that in the explanatory model, where we're not going to have as predictable as an outcome as we do see here, but we can definitely set objectives that we can reach, knowing what type of R-square we can expect to see. So that nonlinear and interaction model also does have the lowest AIC value. So we think that's really the best. And we're going to use, in our example, we're going to consider that we're just going to do this to get predictions. So we're not really as focused on explaining this model or trying to discuss it with the wide audience. Instead, we want to put this model into production, and we want to get values from it on a regular basis. So we do want the best predicting model, the model that's got the most power. So we're going to go with that bottom model, the nonlinear and interaction model. And so here's the model summary. This shows effects when going from the 25th to the 75th percentiles, or 0 to 1 for binary values, or the most common category to other categories. Coefficients come in increments of 1, but sometimes it's more informative to go from the 25th to the 75th percentile. For example, on height. Height can range from a very low number to a higher number in inches. These are young children to early adults. So there's going to be a broad range in those for values in inches. So going from a value, an increment of 1 may not be as informative as saying what's it like when you go from the low end to the high end in terms of height. And then this dashed line, this dashed vertical line that we see, effects above 0 indicate a positive increase in the outcome. Effects below 0 indicate a decrease in the outcome. Effects are significant when the blue confidence interval bar excludes 0. The bars are 90, which is the darkest blue part, 95, which is a slightly lighter shade of blue, and then the 99th confidence interval would be that very light blue line that extends further out. So now we get 90, 95, and 99 confidence intervals in this graph. And we see that for smoking, it's not significant in the additive linear model, but it is significant here. So there probably is a smoking interaction, or maybe smoking represents certain groups, maybe older patients. We're really talking about patients that are in their teens that smoke. And so when we look at age, we see that vertical dashed line does not fall within that confidence interval for age. So we definitely see that as our patients get older, their FEV, or their the amount of air that they exhale, gets higher. The same with height. Now, height actually, when you go from the first to third quartile, which is about going from 57 to about 65 inches, we see a big jump. It's actually close to about 0.9 on the FEV level. So it's important to remember that ranges from about 1 to 4. So that's about a 25% jump. And then when we look at gender or sex, going from male to female, it's not a significant difference. Okay, so now we're going to look at variable importance. The most important predictors of Y have dots furthest to the right and do have bigger F statistics. And that F statistics circled in red in this table, in this output in the upper right. So we see that the biggest, or the most important predictor, the one that gives us the most information about our outcome of FEV, that would be height. And that's followed by age, sex, the age by sex interaction, which is still significant, and we do see smoking status, which in this nonlinear and interaction model is also significant when we have an alpha level of 0.05. In other words, that p-value is less than 0.05. We see that on the right. So it looks like we have a very predictive model, and we see that all predictors contribute some important information in understanding the FEV levels. And so now we're going to look at partial prediction plots. These show trend lines while holding other variables constant at their average value. So now it's important to remember that if we're doing a regression model with 4 predictors, we're going to get, in this example, we're going to get 2 trend lines. And then because we're looking at categorical variables, we're going to see two sets of group tests. As we mentioned early on, we can use categorical and continuous variables in regression models. And when we have categorical variables, it's equivalent of a group test, such as a t-test, or if we have more predictors, it's similar to an ANOVA, an analysis of variance. So we see that on the left side, age shows a moderate effect, but it explodes after the age of 10. So something's going on about 11 and 12 for our patients, where their ability to exhale air greatly increases. And then we see that height has the steepest trend and is the most predictive. So it's important to point out, the steeper the trend, the greater the effect it's going to be. And that it's no coincidence that height is the most important predictor in this data. And then how we can interpret this is that the effect size, while holding other predictors constant or controlling for other predictors, means we use the average for each predictor to calculate other predictor effects. So you've often heard this, that we're controlling for other variables, holding all things constant. And what that means is that when we actually calculate the predicted value for these graphs, we're going to hold, if we want to know what the impact of age is, if we want to look at different values of age and we want to calculate what that effect is, then we're going to use the exact same values in both of those calculations for our other predictors. So here's an example where we have two rows in the bottom of this text box, and they're the formula to calculate the predicted values for one patient whose age is 5. They're 5 years old, and the bottom row would be a subject whose age is 10 years old. So we're going to see the exact same formula. The intercept's negative 4.5. The coefficient for age is 0.007. So the coefficients will definitely stay the same in both of these rows. And since we want to vary, we want to see what the predicted values are for two different ages. We have two different age values here. But for everything else, we're going to hold it constant. So for both rows of data, we're going to use, since we have more boys in this data set, we're going to use the male value. And then it's also the second category. First category is female, and the second one is male. So we're going to use male as our default value. And then we're going to use a height of 62 inches. That's the average height for the sample. So we're going to use 62 times 0.1 in that calculation. We're going to do it for both rows of data for the 5 and 10-year-old. And then we're going to multiply the coefficient of negative 0.1 for the value for non-smokers. We're going to do that in both rows. So when we say that we're holding values constant or controlling for other predictors, this is what we're doing. We're using, when we want to know when we want to estimate the effect of one variable, and we want to vary it using different values for that predictor. We're going to do that for that age, but for all our other predictors, we're going to use the exact same values. We're going to hold it constant. So that's what we mean when we say we're controlling for other predictors. In this formula, we're just going to only vary the one that we're interested in. And in this case, that's age for a 5-year-old and a 10-year-old, and we're going to predict those values. Okay, so we have a significant interaction that shows the gender effect on FEV is dependent on the patient's age. As expected in research, differences are strongest after puberty. So we do see that in blue we see the trend line for males, and in red we see the trend line for females. We see that after that age of about 12, or at around 12, we're going to see that boys and girls differ a lot in terms of their FEV levels. So before that, we do see similar trends, similar rates. But after they hit puberty, and after, I guess, maybe differences in height as well, then we're going to see different FEV levels for males and females. Age is on the x-axis, and our predicted FEV value, our outcome, is on the y-axis. And here's an example of when we want to combine research and regression. This linear interaction model shows a difference between boys and girls. We're not allowing for nonlinearity in this model. We're just giving a linear term for age. We're keeping the interaction, but we're not using the nonlinear terms. So the linear interaction model shows a difference between boys and girls, but wrongly suggests a significant difference starting before the age of 10. So we can see that these confidence bands that are in purple and orange, we see that they separate probably before 9, maybe about 8 or 9 or so. And that tells us the wrong interpretation. Reinforcing the model results with the established research finding that differences begin around puberty at the ages of 12 and not 9 can help, for example, interventions starting at the right age. So rather than starting an intervention too early at the age of 8 or 9, if we go back to a nonlinear model, and we supplement our model with clinical expertise, those familiar with the research would know that if you were to do an intervention, age 12 makes more sense. So here's the model summary. We have FEV equals the nonlinear age times sex plus the nonlinear height and the smoking effect. Smoking effect is significant at the 0.05 level. P equals 0.03. There is an expected lower FEV by 0.12 for patients who smoke after controlling for age, height, and sex. There is a significant age by sex effect. P is less than 0.001 after controlling for other variables. Boys have significantly higher FEV levels beginning around the age of 12. P is less than 0.01. There's also a significant positive nonlinear trend for age, and P is less than 0.001. There is a significant positive height effect after controlling for other variables. There is also a significant nonlinear trend for height. P is less than 0.05. Height is the most important predictor as it has the most predictive power. For example, going from the first to the third quartiles, about 11 inches, increases the FEV by 0.9. And that's about a quarter of what the ranges are in this data set. So in this, we have a model summary, and these are the interpretations of the results. And this is a pretty common way to discuss the regression results, including a summary, including the p-values, and discussing each of the variables in regards to those significant results. And in this, we're going to look at a calibration curve. I have two types. One is a traditional, where we have deciles. We have those 10 groups, and we have on the right side, we have a bootstrapped bias-corrected calibration curve. Using a bootstrapping is really helpful when you have lower sample sizes. So I just want to show you these side by side. The one on the right, we can see it's sort of difficult to see just because of these lines, but we can see on the right that we have we see less calibration on the extreme values, and that's normal. That we're doing a better value predicting the average value than we are at the extreme values. So we have the tails separating a little bit more so from those ideal patterns on both ends. And on the left side, we have our traditional calibration curve. We have what we do with this is that we line up our predicted values and then gather what the average predicted value is for each decile, and then we compare it with the actual average for those subjects that are in each decile. So the red line represents our predicted values, and those blue dots represent the actual data's mean rate for each of those deciles for our different FEV levels. And you can see, because the average are the actual values, those blue dots line up with that calibration curve, the red curve. That's a pretty good sign for good calibration. Both graphs show a very high degree of calibration among all levels of predicted values. And so now we'll cover more on validation, specifically calibration and discrimination. This is a model result that I got from the model validation. We have 4 rows. The top 2 we have 5 rows. The top 3 are for discrimination, and the bottom 2 are for calibration. For calibration, since it's a curve, it has an intercept and a slope. So we want that intercept to be at 0, and we want that slope to be at 1. And for discrimination, we have 3 different measures we can look at for a linear model like this. We can look at R squared, the mean squared error, and the G statistic. And so we're just going to look at the R squared. We see that our model was about 0.807. We had a training and that first column is if we use all data together. The second column is is the training set, and that's if we were to gather some data just for training and then leave out the other part for testing. That's what those 2 sets would be. So the model performed at 0.812 on the training set. It performed at 0.801. Both of them are high. And this is where you usually can just, at this point, just report these 2 statistics. We do have what's called optimism, which is the difference between your training and your testing set. So it's 0.812 minus 0.801. That rounds out to about 0.01. And then you subtract that 0.01 from your original R square, which is 0.807. And so that comes out to be about 0.796. So that's our bias corrected validated R square. But for reporting validation for the split half method, we would want to describe the original full data model results, compare the training and test data results. If dissimilar, what we're seeing above is similar between the training and testing set. But if it is dissimilar, list optimism and the index corrected results. So most of the time you're just going to report the training and testing results for your discrimination and calibration. But there may be times when if you get 2 very different results, and it would be the same if you're doing cross-validation. So the split half method, you're using it, you're just splitting the data in half, but for the cross-validation, you're splitting it into more groups and then creating different training and testing sets based off of those. Say if you're doing 10 groups, you'd use 9 and test on 1 and rotate until you get them all. But in general, you're just going to report the results for the training and testing sets. But there may be times when you do want to report optimism and your corrected R square. And then on the right side, we do have the formulas on how to calculate those. And so now we're going to cover model selection. We have model performance. The purpose is ease of interpretability versus predictive power. We're going to look at a nomogram, which is making predictions easier to understand. And for the linear additive model and nonlinear interaction model, on the bottom we can compare what they look like. So this is something important to keep in mind. If you want to describe this to an audience, one might definitely be easier than the other for that purpose. So we ultimately want these models to get utilized. So you may you may prefer one model for a different situation. And a nomogram can be used to calculate individual predicted FEV levels for patients. It can also be used to demonstrate how the model works for clinical staff. A nomogram works by identifying the points for each predictor of a specific patient, then sum up the points to get the total points, and find the corresponding predicted score in the linear predictor. For example, a 12-year-old boy who is 55 inches tall and a non-smoker has a predicted FEV of 2.25. So besides each characteristic, we have a set of points. For example, a 12-year-old boy would get 19 points for that. His height of 55 inches would give him 20 points, and being a non-smoker would give him 4.5 points, and that totals to 43.5 points. And we'll see that how each of these predictor values lines up with a set of points that we total later, and that gives us a predicted value. So let's start from the beginning. We gather points for each predictor value. And for example, we're talking about a 12-year-old boy. So that first blue arrow pointing up points to an age of 12. And this because we have an interaction, we have two sets of values, one for females up top, and right below it we have it for males below. So we see where that 12 is at. And if we were to go up to the very top row, which indicates the points for each predictor, that's about 19. For height, this boy is 55 inches, so that would go up to about 20 or 21 points. And this child is a non-smoker, so that would go up to about 4.5 points. And so now we sum the total of those, and I think it was 42.5, or I'm sorry, 43.5. So we sum the three values that we had for age for boys, height, and smoking. That comes out to our second step, which is sum the total points, and that comes to 43.5 points. And then we find our linear predictor, and that would be 2.5. And the arrows aren't lined up perfectly, but it would come out to 2.25. So that would be their predicted FEV value. So we wouldn't necessarily do this for each patient, but it's really helpful to show clinical staff how a predicted model works without having to do the math calculation. These calculations are a lot simpler than even using that regression formula that we have. So it's a handy tool. You can just have a paper copy and review with this model, how this model works. And another thing that's important to point out is that the predictor that has the widest bar for points, in this case it's going to be height, that would be your most important predictor. So every increment or every increase of 1 unit or a few points really makes a difference for height, because that really, if you're at your height is 74 inches you're going to have about 100 point on that top row for points. You're going to go, that's the full range, going from 40 to 74 inches is about the same as going from 0 to 100 points for this predictor. So smoking, you can see, doesn't really, being a smoker or a non-smoker doesn't really make a big difference. It doesn't add much more to your prediction. Age for boys seems to have a bigger impact than it does for girls, and that's when we think back to that interaction where we saw boys' FEV values really increase after the age of about 12. That's why this bar is wider than it is for girls. Okay, so what's next? We can select a cutoff level. The pediatric FEV is heavily dependent on age. Most values are interpreted based on age or considered normal if their value is at least 80% of the predicted level. Consider the scenario that you are asked to test a cutoff of 3 based on your predictive model. 4 liters of air is considered healthy for adults. A child's FE level 3 might be considered healthy. Children are given predicted scores based on their 4 predictor values. Determine the area under the curve or C statistic when using your cutoff level and provide consultation on adjusting the cutoff. So here's what it looks like when we set a cutoff at a level of 3. We have on top, we have 2 graphs. We have on top those who actually did meet that cutoff level of 3. Their actual value is 3 or higher. In this we have about 204, and the proportion of predictions that are at or above the cutoff is 0.716. And for this model, if we use this cutoff, our area under the curve is about 0.811. So that's a really good area under the curve level. That's a pretty favorable model for this analysis. And in the top half, we can see the area that is highlighted in green represents sensitivity. And on the bottom graph, we do see circled in red is specificity, and those are true negatives. To the right of that would be false positives. Those are the patients that we predicted to have an FEV over 3, but actually didn't. So these are our false positives. And then we have actually a gray part that's under this output. And this output is our sensitivity, our specificity, false positives, and false negatives. And we do have the false negatives covered up right now. And then we have different sets of predictive values, and we have frequencies for our sensitivity, specificity, false positives, and false negatives. So the model is best at identifying which children aren't grown enough to be considered having healthy lungs yet. Consider using it for that purpose. You can reduce tests and save money. So if we intervene on certain children, we're going to be fairly accurate. Our sensitivity is 0.71, but where we're really good is at detecting those who do not need interventions. So as a cost-saving measure, you can use these regression results to identify those patients who do not need to get interventions. Okay. And so that brings us to what's called a decision curve analysis, and we want to evaluate the prediction model, determine its net benefit, or determine the number of interventions avoided based on our cutoff level. And so the dashed black line shows what the net benefit is when using the model. The red line represents treating all patients, and the horizontal gray line towards the bottom, that would be none treated. In other words, we don't do any interventions. And a net benefit of 0.0973 indicates that the difference between our true positives and false positives will be finding about 10 more true positives per 100 patients using a cutoff level of FEV equals 3. So for every 100 patients we do, if we use a model, that model would give us about 10%. So based on our cutoff level of 3, if we use that, then for every 100 patients we see, we're going to have about 10 more true positives than false positives. And the x-axis corresponds to the percentiles of the distribution of predicted scores. For example, the 75th percentile is 3. This lines up with the y-axis value and a net benefit of 0.0973. So right around, probably around here is where that net benefit of 0.0973 is, and that's roughly about the 70th or 75th percentile. So imagine where that x-axis has 0.75. If we go up, it corresponds to what's the net benefit of 0.0973. If we had a reason to have a cutoff at a value at the 60th percentile, if we go up to where that dashed line meets, that would be at least about a net benefit of 0.20. So that would mean for every 100 patients we see, we would expect to see using our model would give us 20 more true positives than false positives. So you can see the benefit of using the model at these different levels, and once we get to the numbers about above 0.8, there's not a lot of difference between using the model and the all-treated approach. So using a cutoff level that's lower, you may, if it's a costly intervention, you'd probably not want to intervene on more and more people. You'd want to intervene on less and less people. So it could be costly in terms of how much the actual cost in dollars, or it could be costly in terms of some interventions have serious health side effects, so you wouldn't want to use it there. But if the intervention is cheap, there's not a lot of side effects, then you can probably use a higher threshold. You can use the intervention more often, and that will give you a higher net benefit. These are in this slide, these are interventions avoided. I mentioned that this model is really good at predicting who doesn't need an intervention. So because we can find the net benefit, we can also find the amount of interventions avoided by using this model. So in this, we can avoid about 58 of 100 unnecessary interventions with a cutoff of 3. The reason is the model has a high specificity level, and the majority of patients won't have an FEV over 3. The volume of higher patients on the lower end gives more opportunity to avoid interventions. Okay, so now that brings us to explanatory models, and we're going to look at hypothesis testing on very low birth weight. We're going to do risk adjustment and sensitivity analysis. For the very low birth weight study, the N is 189. It's a small data set. The predictors are birth weight in grams. The outcome is birth weight in grams, and the predictors are age, being a smoker or not, FTV, which is the number of visits to the physician, the weight at last menstrual period, the number of previous births, PTL's premature labor history, HT's history of hypertension, and UI's presence of uterine irritability. And so here are our descriptives. You can study these to get an idea of what we're going to see. Here's the model, and it's birth weight equals age plus smoker plus last weight, FTV, parity, PTL, history of hypertension, and uterine irritability. And we see how we can interpret the results. For every pound increase in mother's weight, there is an expected increase of 4.0 grams. And this is for the predictor LWT. That the coefficient is 4.01. And when we look at smoking, if the answer is yes, they are a smoker, the smoking rate is a health outcome. We would definitely consider the smoking rate a health outcome worth improving. And then key predictors in research, smoking, hypertension, and UI significantly reduce birth weight by 234, 587, and 559 grams after controlling for other variables. So we see smoking, it's negative 233, height, RHT, history of hypertension is negative 587, and UI is negative 559. And we can see on the right that these are significant predictors for the things that are for the predictors circled in red, as well as LWT. For categorical X, a reference group is compared with each level. For example, PTL equals 0 versus 1, 0 versus 2, and 0 versus 3. And these are the results we see in the output. Now we're going to look at the model summary. Again, these show the difference from going from the 25th to the 75th percentile, 0 to 1 for binary values, or the most common category to other categories. So we can see that values are, we can see point estimates and confidence intervals to the right of this vertical dashed line show effects that are expected to increase a baby's birth weight, and for the things that are below, that would be things that we would expect to reduce a baby's birth weight. For example, smoking. For mothers that smoke, we'd expect their babies to have a lower birth weight. As well as hypertension and uterine irritability. And when we look at variable importance, the most important predictors of Y have dots furthest to the right. So we see that uterine irritability, let me see what PTL is, premature labor history, so premature labor history, history of hypertension, last weight, those are all significant predictors, as well as the smoker indicator. And but in this variable importance graph, the predictors on the bottom are also the ones with the dots furthest to the right, and those are the most important predictors. And we have partial prediction plots, and these show the trend lines while holding other predictors constant at their average value. We can see more on those trends, and we can see which direction they point to. Parity may not be significant, but let's look at LWT, last weight, on the bottom right. We see as weight increase, mother's weight increases, so does the baby's weight. And for history of hypertension, we see those that have the history have babies with lower birth weights, as well as uterine irritability. We see mothers that indicated yes also have lower birth weights. And so now we're going to look at our model selection. The more complex models don't validate well, choose the simplest model for reliability and interpretability to your audience. So unlike the last model where we're specifically interested in just model predictions, for this it's an explanatory model, so we want to explain it to our audience, explain it in our research. And so what I'd probably recommend would be a linear and additive model. In this hypothetical example, we're going to be explaining it to staff and maybe to other researchers. And so we'd want to have a model that has a greater shot at being utilized. And so our linear model has an R-square of 0.226. Its validated R-square took a dive, and now it's at 0.102. It does have the highest AIC model, or AIC value. So I would also consider that interaction model that has the interaction between age and smokers. We see that that mothers that do smoke have a big drop in baby weights over time. So older mothers that do smoke have a significantly lower baby birth weight than mothers who didn't smoke that were the same age. For the youngest mothers, there's not a big difference between mothers who smoked and didn't smoke in terms of the baby's birth weight. But for our oldest mothers that were smoking, that you do see a big gap there. So if there was an interest in that subject, or if that was a concern, I would say use the second model. But we're using a hypothetical example where we're just interested in the easiest model to explain. So that would be the linear and additive model in this example. But I would also consider that interaction model between age and smoking. But I wouldn't recommend the nonlinear models that are additive or have interactions, because that validated R-square doesn't really hold up as well. So in a bigger data set or in future data, we wouldn't expect it to hold up as well. So in this case, we can now do a sensitivity analysis. Once we have the regression coefficients from our model, we can calculate how the birth weight rate can change if we modify the distribution of our predictors. For example, what would happen if we cut the proportion of smokers in half? We can identify the predictors that give us the biggest bang for the buck in performance improvement. We can also eliminate factors that are unlikely to help improve outcomes, therefore saving resources. This is a tornado plot. It shows the predictors that the outcome is the most sensitive to at the top as standardized coefficients. Although not the most important, the mid-range smoker variable may have a clinically relevant objective of reducing rates. So the predictor that had the biggest impact on the outcome was the value for uterine irritability and then a history of hypertension. So those were the two most important. But the one thing that we might be able to modify would be smoking behavior. That's a difficult thing to do, but there may be ways to do that with uterine irritability as well. I'm not sure, but hypothetically, if we wanted to focus on smoking, that would be something that we can probably modify. And so we will do that with the sensitivity analysis. So we have two graphs here. And for low birth weights that are less than 2,500 grams, what if we reduce smoking from 40% to 20%? So in a sensitivity analysis, we get our regression coefficients. We begin to create simulated data sets. So now we create a data set of our own based off of a distribution that we think is likely. For age, we might keep the distributions the same for age. But for smoking status, we might modify that. So in that first set of data in our data set, on the first graph, we see that 40% of mothers smoked. So that was the data that we were looking at. So we're going to kind of think of this as a before. And on the right side, we modified our data set so that 20% of mothers smoked. And so on the left side, if we had 40% of mothers that smoked, and our goal was to have birth weights that were above 2,500, we'd see that when we have 40% of mothers who smoked, we see that 12% of babies are born at a low birth weight that's under 2,500 grams. But say if we modified, say if we changed our data set so that we now have only 20% of our mothers that smoke, then we'd have 9% of babies born at a low birth rate. So we would reduce the amount of low baby birth rates by 25% or 3 points. So we'd consider that we might consider that an important improvement, but clinical staff may or may not consider the reduction in low birth weights worth the resources to pursue. So by going with this strategy, they might not find that would be a great way to reduce baby birth weights or reduce the occurrence of low birth weights. They may or may not, but with this sensitivity analysis, we can show that by modifying behaviors or health practices or unhealthy practices, we can show an improvement in the occurrence of very low birth weights. Okay, so that's it for our explanatory model. We'll continue here next week for our second case study. I'm going to go ahead and show just a quick peek. And I'll also show a little bit of how to use the my Shiny app, my GUI. I'm going to quickly do the FEV study. So on this tab, I can upload the data. I've done that already, but then I can go to number 1 in the Model Builder tab, enter in the data set, switch that to no. For number 3, I'm going to put in my outcome. I'm going to put in my predictors, age, height, sex, smoke. I'm going to add my nonlinear terms, height and age. Turn that to yes. A lot of the defaults in my Shiny app you can just keep. And just a few things you would need to change. We want to update the model, yes. We're going to add the interaction between age and sex. And then now we're going to run the model. The model is run. Here are the regression results. That's that R-squared 0.807. We're going to go to the summary. It produces a summary there that tells us in what direction the predictors have on the outcomes. This gives us some variable importance. On the bottom we see height's the most important predictor by far. We go to our partial prediction plots. We see those trends and those group differences that we looked at earlier. We're going to go down. Okay, so it's asking for, since we did an interaction, we're going to put in that interaction. We're going to see those 2 trend lines for males and females. We're going to add confidence intervals. We're going to change the lines to red and blue. So that completes that graph. We're going to create a nomogram. For example, we can see that here's the age. We looked at a boy who's 12. That's about 55 inches tall. That's a non-smoker. And we can see that would come out to be about 2.25, a predicted FEV level of 2.25. We're going to look at calibration. I'll just use these default. I'll do the bootstrap actually. That gives us the calibration curve we looked at. I'm going to go back to the Describe tab. I have a default function called calibration curve that you can just copy the text right here, enter it into number 1, turn number 2 to the graph option, and it produces that calibration curve for you. So that's the traditional calibration curve. Now we're going to look at model validation. I have the option to do a bootstrap, which I did in the actual study, but I'm going to leave it to cross validation. I'm going to change that to 2. I can leave it at 10. That's a real cross validation. 10 group cross validation, 10 set cross validation, but we're going to leave it at 2, and that's the split half model. So we're going to enter yes, and that'll give us the validated R squared 0.792. I did a bootstrap in the earlier one, but here's these settings give you the split half validation. And we're going to go back to the Model Builder tab. I'm going to scroll down, and I'm going to select a cutoff level of 3. I'm going to keep the other defaults, and I'm going to go to number 7, click yes. That gives us the graph we looked at earlier, as well as our sensitivity and specificity values. We also have the net benefit down here, but I do have the curve. I'm going to leave it at the default for number 1, and we're going to do a net benefit curve. Okay, so that produces the decision curve analysis, and if we want to know what's it like for interventions avoided, we switch to that, and that gives us that decision analysis. And so that is it. Okay, and then I'll